Hello everyone. Today I want to talk about an analog technique that is very useful for increasing the slew rate. So assume that we are going to design a op amp, and maybe we are going to use that op amp as a comparator. So we have an op amp with a current source. This is going to be a NMOS type of op amp, which is a differential. Oh, sorry, which is a differential circuit, and then we have these two PMOSs as loads. So and so these are PMOSs, NMOSs, and this is VDD. Oh, VDD, and I'm going to okay, and as you can see, we have two differential input, and this would be the ground. So, and we have the next stage. This is the single-ended op amp. So we have this the second stage, which could be NMOS with uh, with a load that should be a PMOS load. So this is the, as you can see that we have inverting, so this will be the positive input, and this one will be the negative input, and this is the output with for example capacitive load. The problem with this kind of a op amp and the idea is very conventional, is that for example in the stage that we are going to uh, out assume that we are going to charge the op amp, and this guy goes up and this down, so this one will go down, and as you can see this one going to be off. Let's name that M, I don't know, O1, and O2 as O as output at the out. So as you can see, when this guy this one going to be off, and this guy going to the MO2 going to discharge the capacitor, the going to charge the capacitor, the charging will be limited to this bias over here, and will be limited to biasing of this transistor. So the quasi-floating gate, if I remove all of this and go back to M01, I'm going to be better in next session with the drawing and everything. As you can see, the charging is limited. You saw that. So the idea is to the idea of quasi floating gate, which is very let's say viral nowadays in analog circuits and in op-amp designs, and I use that in a paper, and you can see the difference. You can see that this is the you can see the effect of phenomena. uh, so if you use that, so the idea is instead of the let's say constant biasing or stable biasing, we use a capacitor between these two, and when this goes up, this down as a differential, so this one will be down. This is a common source, and so this one also goes down, so the biasing will not be constant, and so MO2 can charge the output with uh, with I want to say not very limited uh, with not very limited current. So the current of this one MO2 will not be limited to the bias over here. For assuming that this is, for example, in the last case, without the capacitor and without the idea of quasi floating gate, we have 1.2, and this is 1.8, very common in in 180 nanometers design. So when this one is stable, so we have the gate source like 0.6 gate source, and the bias will be limited kind of to this kind of but when this one goes down, so it's going to be 19.9, even maybe point, I don't know, for example, this is a very high impedance node, so maybe even 1.1, sorry, 0.1. So the gate source will change. Okay, so will not be this number. In quasi-floating, the gate source will be numbers like this, and maybe even 1.1, and etc etc. This is 1.1, and the voltage this is not 1.1, this is the gate source difference, but this node can goes down to the numbers such as 0.1. So this is quasi-floating gate, as you can see, and because when this one goes for example down or up, and this one goes up, this capacitor could discharge the charge over the biasing over here. So the idea is to use a very high impedance pseudo resistor instead of attaching them with like in conventional way, you can attach them with a very large resistor, like in order of giga ohm. So and this guy cannot discharge, and here also is the gate of the transistor MO2. So as you can see, the variation over here will be, sorry, this not goes up, the variation over here will be over here, and we have a significant effect on the slew rate. So and because you cannot you can, but it's not very good idea because of the sizing and everything, to have a conventional resistor over here, like if you add something like that, it will be very big, and maybe it's not even possible if you use a technology over here. So instead of that, it is a common sometimes to use a transistor. You can use a transistor instead of resistor in different regions. For example, if this is this this is a NMOS transistor, so the gate source is zero, so no current over this transistor, so this transistor has a very large resistance. Also, you can use transistor, this is a side note, that you can use resistor for in triode the ohmic behavior of a transistor in triode could help you to design design resistor with lower amount, not in the order of giga ohm or something like that, but they will be very they will change with any things like the variation in the corners and temperature and everything. I'm not going to talk about that. So instead of a resistor, you are going to use a pseudo kind of a resistor, a big resistor that do nothing, and it is better to use PMOS because of some reasons. So I'm going to add a PMOS. So this is a PMOS, and then you have the bias over here, and you are going to connect the gate source of the transistor to be in a cutoff region and act as a actually a very big large resistor. If you search for quasi-floating gate on the internet, you will find the quasi means like it's not real, it's like a floating gate. It's similar to floating gate. I use that in a paper. You can see my paper. I'm actually going to show you. It takes time, but it's kind of okay, I'm going to show you my paper. So I'm going to my Scholar. Cannot see that part. So my profile, and as you can see, I use that in a paper. I do not remember the name of the author that used that technique the first time, but I know they are in Spain, I think in civil university. So I'm going to show you the name of the authors that first time used that. So I'm going to like search for the quasi-floating gate. Quasi-floating gate. So I'm sure that okay, maybe one of these. Oh, let's go to 6 to 10 and 6 oh, what is that? uh, I'm not sure. I think might be one of these, maybe this one. For you to tell you that when you use this technique, assume that you do not have the quasi thing, so your slew rate, if you have a like square wave in the input, this is the input, so the output will be something like that, very slow. So assuming that you have quasi-floating gate with quasi-floating gate, you have something better, sharper, and very close to the input. And this is these are outputs. I become better with this electronic pen. So this is series of video analog technique, a very simple analog technique will help you really. This um, also now I'm working on something else. This helps me. So do not forget about analog technique. I will add other videos to the channel very soon about the other techniques like FVF, or how to make the input impedance less or output impedance more. Things, simple things, but very useful and very helpful techniques, easy to understand later. So okay, so I'm going to stop the recording. Thank you very much. Oh, not that. I should go to, okay. Okay, thank you very much.